Welcome to lecture number 10 in the Structural Dynamics course, and today we will finalize our two-lecture session on damping of structures. So last week we considered local dampers, in particular local viscous dampers, placed both on a cable but also on a more general fine element structure. And today we're going to look at a very significant type of damping device that is used in many contexts, in particular in larger civil engineering scale structures. As we'll see, the so-called tuned mass damper, or just the TMD. The TMD is in particular effective when the structure is excited at resonance at a particular frequency, namely the resonance frequency of the structure. That means a loading that exactly excites one of the vibration modes of a general flexible structure. We will start out by deriving the principles of such a tuned mass damper, and then we will immediately derive the frequency equations. That means we are in the frequency domain, assuming harmonic motion. So we will consider dynamic amplification factor, the frequency response function, and everything in the so-called frequency domain. And that means that a TMD is actually only calibrated with respect to not the transient part, but with respect to the steady state part that we will end up with once the transient part has been eliminated, and we are going to wait until we reach steady state. So the TMD wants to bring down this steady state amplitude A. That's the agenda of today. And for that, we'll conduct a frequency analysis. We'll find the optimal frequency tuning, that is basically the stiffness of the TMD, and we will make sure that the optimal damping, that is the viscous coefficient CD for our TMD, that this will bring down the so-called structural amplification factor, which is the DAF that we considered earlier in lecture number 2 for harmonic motion of a single degree freedom system. So everything boils down to minimizing the steady state amplitude using the tuned mass damper. A few introductory remarks. We will obviously consider lightly damped structures. A very small for the structure, much smaller than 1, and maybe in the order of 1%, but in some cases also down to 1 per mil. So lightly damped structures with a very small structural damping ratio, because in that case we will have large vibration amplitudes when we have a loading acting near resonance. Remember that at resonance the dynamic amplification factor can be measured as 1 divided by 2 zeta structure, so the structural damping ratio. So this will be 50 for 1% critical damping, and 50 is a large dynamic amplification factor. So we would like to bring this number down, and potentially down in the order of 5 to 10, maybe 15. So at least a reduction by a factor of 2, potentially also 4 and 5 of the dynamic amplification factor, of course depending on the amount of the structural damping. The TMD works by an additional mass, here referred to as M. So of course the structure is as we know it, and let's assume that the structural mass is M0 and it is suspended by a spring with stiffness K0. Then we attach the so-called tuned mass damper, and it contains the oscillatory or vibratory mass or secondary mass M, and it's attached to the structure by a spring with stiffness K and a viscous dashpot with viscous coefficient C. So let's assume, for instance, that we have a shear frame building. Could look like this. And we want to damp first vibration mode. We need to choose a particular vibration mode for our tuned mass damper. In many cases with environmental loading, it's typically the first vibration mode. So first of all, we would like to place the tuned mass damper where it excites or where it has the largest amplitude to act upon, and that would be for the first vibration mode at the top floor. So we install our TMD with M, K, and C, so that when the structure vibrates forth and back, the TMD will as well vibrate forth and back. And the idea is to amplify the TMD deflection so that we maximize dissipation of energy in C. That is the idea, the working principle of a tuned mass damper. Now, what's the link between our simplified structural mass M0 and the flexible structure to the left? Well, basically M0 is equal to modal mass, K0 is equal to modal stiffness, and that means we need to calibrate K, C, and M corresponding to these modal parameters. And remember that this calibration depends on the normalization of your vibration mode. So, like we did earlier in the course, we normalize the maximum vibration amplitude, or the vibration amplitude at the position of the TMD, to unity, and thereby M0 and K0 become the equivalent structural parameters. So that is the link between the flexible structure to the left and the idealized structure, single degree of freedom structure, to the right, where we have attached our TMD as a supplemental degree of freedom with mass M. To the right, we have a also representative model, a structural model. In this case, we only consider a single story. So again, this single structural model here is representative of the full flexible structure. So K0 is the mode, modal stiffness, M0 is modal mass, and then we attach the TMD. So the tuning principle is given by the 3 bullets and at the bottom of the slide. So first, choose your absorber mass and choose sufficient mass to generate the desired performance. We will have some design formulas at the end of this lecture that gives you that enables you to design or to choose M to get the desired performance. Once you've got or chosen M, you will then afterwards have to choose the stiffness K of the TMD, so that the TMD is in optimal resonance with the structural mode you want to damp. And finally, we want to extract as much energy as possible by the viscous dashpot in the TMD. So it is a 3-step procedure with M, K, and at the end C. What is worth noting is that the tuning of the spring mass, that means these two here, they are extremely important, because we need the TMD to be in exact resonance, synchronized with the structure. So thereby we get the best interaction between the two devices, namely the structure with M0 and the absorber with M. Then afterwards, there are principles to find C, and there are actually quite a number of them, and it really doesn't matter which one you choose. I'll present one that we have derived recently, but there's also a classic procedure or classic value which many of our colleagues use. It's really not that important. And finally, you should note that although we refer to this device as the TMD, as a tuned mass damper, if you go into other disciplines, mechanical engineering, for instance, physics, you will have the tuned mass absorber or the dynamic vibration absorber or other names. So this type of device, also, although the same, will be referred to with many names in the literature, in standards. So remember that. These days, if you're going to build a pedestrian bridge, you will have to install dampers. Pedestrian bridges nowadays are really slender. Have a look at the bridge to the left. You have a very nice and slim deck structure. Almost no height of these box girders. Then you have fairly slender arch, and you have the cables supporting the very slender box girder by the so that it is supported by the arch. So in principle, or in general, pedestrian bridges are what we refer to as slender. So they're really prone to dynamic amplification. For instance, people walking on the bridge. So it could be by walking, the Millennium Bridge scenario for the opening day, but also running, marathons in the city of Copenhagen or Berlin in this case, and bridges should of course also be comfortable with respect to running. So for many bridges, it's initially the vertical displacements that are a problem. As you can see underneath this bridge, you have installed these green devices. devices. They are probably easier to identify on the bottom picture here. So let's assume we have our bridge deck, and we have K staples and part of the arch up here. We install physical mass, green physical mass, and we suspend it to the structure by springs, and we then also install a viscous dashboard. So without the TMD, we will have very large deflections of our bridge when, for instance, people are running across the bridge. Now, once we have installed our TMD, the TMD will make sure that the deflection of the bridge deck is reduced significantly, but it is at the cost of very large TMD deflections. So when people are running across the bridge, they will have no problems with comfort, but underneath the bridge, the TMD will vibrate heavily, and of course there should be space enough in here to accommodate for these large TMD deflections given by an amplitude. So make sure there's room enough inside your structure or here underneath your structure to allow these large TMD amplification or amplitudes. Chimneys are prone to vortex-induced vibrations by wind, so we will have vibrations forth and back because of the wind actuation. And at the bottom, at the suspension of towers, we can install so-called viscous dampers. Those are referred to or addressed in our lecture number 9. But we also have pendulum-typed TMDs. So at the top, we will have ring TMDs surrounding the tower. So you can see part of the ring up here, and they are connected to some higher point on the chimney by a wire. And that means if we have vibrations forth and back, we will see that this ring will vibrate forth and back and thereby deflect damping devices. This is not a damping device, but it could be. That will then dissipate energy. And the stiffness of the TMD is then given by the pendulum length. The mass of the TMD is given by the ring mass, and the damping is given by the viscous dampers you then install between the ring and the chimney itself. And let's just remove these D's because the notation does not include a subscript D for the TMD parameters. The equation of motion is conveniently determined by an energy balance principle. But before we address this, let's just recapture that the structural mass, we always consider that in the back of our head as the modal mass of an underlying flexible structure. We never build structures with an M0 or K0. This is an ideal structural model, and it represents the modal mass for a particular vibration mode. Typically, for most structures, the mode 1 is the one we want to address. And then K0 then correspondingly refers to the modal stiffness. And we, in the calibration of our TMD, that means for the tuning of the TMD, we simply neglect any structural damping. In real life, the structural damping is anyway small, because if it wasn't small, there's no need for a TMD. So whenever we need a TMD, it's simply because the structural damping is very small. And therefore, in the tuning of the TMD, we neglect this. So remember that the modal mass is obtained for a vibration shape that is normalized to unit modal mass. That means that Uj, M, just a little bit ahead of myself here, Uj is equal to 1. So make sure, of course not. So we have that Uj multiplied by some kind of connectivity vector is equal to 1. And that's the mathematics, but Uj is 1 at TMD location. This is simply the normalization that we need to find the representative modal mass and modal stiffness. So in the model to the left, we have introduced some properties. And first of all, we introduce x0 as the absolute motion of the structure. And then we add xd as the relative displacement of the TMD. That means the elongation of the stiffness k and the damper c. So xt is simply the relative displacement of the absorber mass, and that means that the absolute motion of m is equal to x0 plus xt. Then we can set up the kinematic and potential energy, and we know that our equation of motion, our equilibrium equation, means that the corresponds to the mechanical energy, the time derivative of the mechanical energy should be equal to minus the dissipated energy, and also including power by external work. So the kinetic energy is equal to the mass of the structure multiplied by the velocity of the structure plus the mass of the TMD times the absolute velocity of the structure, and this absolute velocity here corresponds to the time derivative of this absolute motion. So kinetic energy is always based on absolute motion. However, potential energy corresponds to deformation. That means that is due to relative motion, also referred to as deflection and deformation. So we deform the structural spring, so that provides us with the potential energy K0 times the deflection x0 squared. And then we also deform the TMD spring, and that is K times the relative displacement squared, that's this xt squared. On the right hand side, we have dissipation of energy by the viscous dashpot of the TMD, and that's c times the velocity xt squared. And if we have any external loading, F, it's multiplied by the velocity to provide the work or the power produced by this external loading. When we then substitute these expressions into the energy relation and we perform the differentiation, then we find out that some terms are multiplied by x0 dot and other terms are multiplied by xd dot. So those we collect in two major terms, and the first term, and what is important is that on the right hand side we have equal to 0, and because this equation 10.3 should be equal to 0 for all times, then the first parenthesis should be equal to 0 and the second parenthesis should as well be equal to 0. So from that we get two equations governing our two unknowns, x0 and xd. And these two equations are given here. So if you go one slide back, you will recognize this one coming from x0 dot. And what was inside here should be equal to 0. The external loading is then moved to the right hand side of the equation, whereby the left hand side only contains our 2 degrees of freedom, x0 and xd. The second equation here comes from the other parenthesis we have here, with that contain a common factor xd dot. So therefore we get these two equations. Now it's also fairly easy for this simple system to actually just set up the governing equations for m0 and m. Let's make a small sketch here to the right where we have the m0 mass. For the m0 mass we will have a positive deflection upwards, and let's assume that we have a corresponding, it's not u0, it's of course x0, and we have x0 plus xd of our top mass, or TMD mass, m. Now let's assume that x0 is positive, whereby m0 will move upwards. Then we have a spring underneath, restoring this deflection, and the force is k0, and then just x0. Between m0 and m we have a spring and a dashpot. Let's have a look at the spring first. If x0 is larger than the deflection of x0 plus xd, then we will compress the spring, so it will exert a force that is positive downwards as well, and it will be k x0 minus, or simply xd, sorry. Yes, xd. And we will as well have a deflection. And remember that xd is positive upwards, so we need a minus on front because we have compression. And we will also have a force minus c xd that acts in that direction. And then of course we will have some kind of external loading F on our structure. So the force equilibrium for M0 says that M0 x dot or x0 double dot, we will then have restoring forces from K0, that's from the bottom spring, and then we will have negative restoring forces from the other springs, and that will provide us with minus C x dot minus K xd, and on the left hand side we will have F. So this is simply by vertical force equilibrium on Newton's second law. And if we apply those, we will get this expression here in 10.6, and we can set up a similar expression for the TMD mass, and thereby we get a different set of equations, but these two must of course be the same. So what we see is that the first equation in the energy balance is simply obtained by the sum of the two equations in 10.6. So the idea is here that you can create any linear combination of the two equations of motion, and that relates 10.5 and 10.6. So it's really up to you to choose which of these formalisms you want to use to find your equation of motion. In general, of course, M0 and K0 are known values from modal analysis, whereas our task is to calibrate M, K, and C of the TMD so that we get optimal viscous vibration reduction. That means maximum or the best performance that we can get from the TMD. Or in many cases, sufficient performance, because the more mass you add into your TMD, the more expensive it also becomes. So there's also a commercial side of the analysis. The idea is now to convert these two equations of motion into the frequency domain so that we can do steady-state analysis. The idea is to assume harmonic loading of our structure. And this harmonic loading is in reality in a time simulation represented by a cosine or a sine function. But in frequency response analysis, it's convenient to consider a load magnitude f, real value, and then multiply by the fully complex harmonic solution, the exponential function to I omega t. And then we wait until steady state. So this symbol here indicates wait until steady state in this case. And during steady state, the response of the structure will be harmonic as well. Same frequency, but with a different amplitude. And there can also be a phase delay, so therefore x0 will be a complex number. But now we also have a second degree of freedom, and it is represented by a complex amplitude xd. But steady state claims that we need to wait until the frequency is the same. So we can assume these three fully complex exponential solutions, and we would like to substitute them into our equation of motion. Let's, from the energy balance, take the first equation of motion. That was the one derived for the structure energy relation or energy balance. So now we assume that we have harmonic force, we have harmonic structural displacements or response, and we also have, look with a D, harmonic TMD response. Let's consider x0. So when we differentiate x0, we need to differentiate the argument of the exponential function, gives us I omega, and then x0 exponential function I omega t. And if we differentiate once more, we get the acceleration. That gives us another I omega. And I squared is equal to minus 1. Omega squared is omega squared. x0 I omega t. And the same thing for xd. So if we substitute that into our equation of motion, we will get m0, and then we have minus omega squared x0, and then exponential function I omega t plus m minus, write the same thing once more. We'll have another n, but this time it's with respect to xd, and then k0, x0, I omega t, and f like this. We can cancel all the exponential functions, and that means that we can collect our solution in two terms. A first term where we collect everything that is proportional to the structural amplitude x0, that is the two first terms, and we also have a stiffness term. Then we have a second term where we actually do not need plus, because the xd term only contains the minus, so it's minus omega squared m xd, and we will have f on the right hand side. So this is our first frequency equation. Our equation of motion for the mass is m x0 double dot plus m xd double dot plus c xd dot plus k xd as function of time equal to 0. So really careful putting in these as function of time arguments to indicate the difference between the time domain and the frequency domain. Now, what have we learned? If we have an acceleration term, it's the same thing as multiplying with minus omega squared. If we have a stiffness term, it enters the equations as itself. So in between, of course, we have a damping term, but a damping term is proportional to velocity, so the damping term should simply be multiplied by I omega. So I believe that for this second equation of motion in the time domain, we can simply write the frequency version directly, because we collect everything with x0, that's the first term, and we can write it as omega squared mx0, because we know acceleration is simply a factor minus omega squared. And then we have three terms with omega d, that means I make a parenthesis, and the first term is an acceleration term, the second term is a damping term, and the third term is a stiffness term, xd equal to 0. So it's really fast to go from the time domain into the frequency domain once you know how it works. And this provides us with these two frequency domain equations in equation 10.8. Now, we would like to minimize x0, or actually it's the absolute value of x0 that we want to minimize by the TMD. But again, our concern is also not to get a too large TMD deflection, because inside the housing of the structure, inside the bridge deck, we also need some space for the TMD. Consider you have a pendulum damper inside an offshore wind turbine. There's only a limited amount of space. The radius is actually the maximum vibration amplitude of your pendulum. So in many cases, this is also a concern. But this is the structural deflection is our main objective. And next, we would also like to minimize xt. Now that means from these two equations of motion here in 10.8, we need to isolate x0. So one way to do that is to find xd from the second equation, eliminate xt in the upper equation by this expression, and that means in the upper expression we then only have x0 and f as variables. So we collect we isolate x0 on the left hand side and keep all other terms on the right hand side, and then we divide by f to get the ratio between amplitude, response amplitude, and force magnitude. And that provides us with the frequency response function of our structural degree of freedom. Then we can plug this expression back into the second equation here to eliminate x0, and then we can find xd, and this expression looks like at the bottom of the slide in equation 10.9. So now we have two frequency response functions, one main function for the structural degree of freedom, that's the one we initially want to minimize, and we would like also to minimize this secondary equation representing the amplitude of the TMD. it is, as always, convenient to normalize our structure. So first of all, we can divide by m0, and thereby we get the natural frequency, omega 0. It's also the modal frequency for the mode we want to damp by the TMD. So this really defines the structural parameter. Then the magnitude of the TMD, the size of the TMD, is determined by its mass, and when we divide by the modal mass, then we get a mass ratio. So this mass ratio really determines the size of our TMD, and basically also the cost of the TMD. So we should choose or select the mass ratio so that we get sufficient performance of our tuned mass damper. The stiffness is then conveniently represented relative to this TMD mass. Then we have stiffness or mass that defines a natural frequency, and we give this natural frequency a subscript d to represent damper, or TMD as tuned mass damper. And finally, the viscous parameter of the TMD is then normalized similar to how we found the damping ratio for a single degree of freedom system, and that gives us the non-dimensional damping ratio zeta d for the TMD. So these three parameters are the three TMD parameters to be chosen. And actually we only choose the mass, and based on the TMD mass we can then obtain an optimal stiffness and an optimal damping parameter. And of course we cannot determine these non-dimensional or these dimensional parameters or normalized parameters as we like here in 1010. Of course they come out naturally once you normalize your frequency response function, in this case by the modal stiffness, the structural stiffness K0, whereby we get the so-called dynamic amplification factor. That's the amplitude, dynamic amplitude of the structure relative to the static amplitude, F divided by K0, if we neglect any dynamics, and that this ratio then defines the so-called dynamic amplification factor or dynamic magnification factor. And it turns out that the parameters in 1010, they enter this normalized frequency response function as its natural governing parameters. And the same thing, the same procedure we can use to find a so-called dynamic amplification factor or frequency response function for the relative TMD deflection. So again, our main objective is to minimize the amplitude x0, but it would be nice to also have a minimization of xd. And of course, we want to do that at resonance. That means for response frequency, loading frequency, steady state frequency, omega very close to the natural frequency of that particular mode, omega 0. For our 2 degree of freedom model containing the response of the structure and the response of the TMD represented by xd, the natural frequency omega 0 actually never appears as a representative frequency, because let's assume that you let c approach 0. In that case, the dashpot disappears, but you will still have a 2-DOF system with 2 natural frequency different from omega 0. However, in the opposite limit, where c approaches infinity, the viscous damper becomes rigid, and that means you will obtain an equivalent system corresponding to a total mass of m0 plus m, supported by the structural spring K0. And the natural frequency for this system we will refer to as omega infinity. So for large damping, that means c approaching infinity, or simply the damping ratio zeta d approaching infinity, the relative motion xd tends to 0, and therefore the total mass will be the sum of m0 and the TMD mass supported by K0. So this infinite natural frequency that we refer to as the locked damper frequency is given by the original structural spring stiffness, but now divided by m0 plus m. So when we divide in the numerator and the denominator by m0, we will get omega 0, the single degree of freedom structure in the numerator, but it is reduced by the square root of 1 plus the mass ratio mu, which is larger than unity, and therefore omega 0 will be larger than omega infinity, or conversely, omega infinity will be slightly smaller than omega 0. And this infinite frequency turns out to be a reference frequency for our TMD structure system. Let's go back to our frequency response function. And in the following, I will draw frequency response functions or dynamic amplification factors. So I'll take the absolute value of x0. And such a curve you will see in the graph to the left, representing structural vibrations, where we will have the absolute value of x0 normalized or divided by the static deflection. So we'll have dynamic amplification. And the three curves represent three different values for xd, and we choose 5% for the mass ratio, which is quite large in many cases, but still within the realistic range. So we choose 5% here to get nice curves and get a substantial reduction in our system, but in most applications you could also go down to maybe 2 or even 1% mass ratio. So the three curves, the dash dotted curve represents zero damping. We will have one curve with 10% TMD damping and one curve with 30% TMD damping. And be aware that you do not convert the TMD damping into structural damping. That would be nice, because then it simply mean increase C to D as much as possible. That's not the case. Everything is a question of balance. We need to find the right balance for the TMD damping. And you may see in the three curves, the black, the red, and the blue curve, that they actually intersect each other at 2 points. First point, A, is to the left of resonance, that is unity in this curve, and the other point, B, is to the right. So we have one neutral frequency below 1 and one neutral frequency that's above 1. And these points, A and B, seem to be independent of the choice of C to D. And because they're independent of the damping, they can be used to calibrate the stiffness, that means omega D, or simply K. So next, we would like to choose omega D so that the dynamic amplification factor at A is equal to the dynamic amplification factor at B. And the reasoning for that is that if A is larger than B, then the structural response will be dominated by this peak here around A, and conversely, if B is larger than A, then we will simply have a peak in B, and we do not want any peaks. We would actually like to have, ideally speaking, a flat plateau at a certain level, like this, so that along this flat plateau we do not have any peaks or drops, so we have a constant amplitude level. And this, of course, we would bring down as much as is needed to stay below maybe fatigue limits or comfort limits for our pedestrian bridge. And of course, for the blue curve, point B satisfies this condition, but for point A, we have a peak that is above. So it's like a waterbed, if you remember that. If you push down at one point, it will go up at another point. And the question is, of course, to find the optimal balance. To the right, we show the amplitude of the TMD. And you can see for the TMD, there's also a single crossing point that is independent of the damping. And this point C actually corresponds to the locked frequency. And you can see it's slightly below omega 0. So here at this point, we have omega infinity divided by omega 0. And the idea is as well, for the TMD, if possible, could we get a flat plateau in this case to avoid this overshoot, for instance, by the blue line. And we already have an indication for XD. It's simply cranking up the TMD mass. So it's quite easy to get the condition satisfied for XD. The problem is that in the limit we get omega 0, then we simply attach the TMD to the structure because our viscous dashpot becomes too rigid. And at omega infinity, we do not get, or we will get, in many cases, very substantial overshoot in our X0. And remember that this is our main concern, and to the right, we only have a secondary condition. It would be nice to also get this reduction in XD. Now the frequency response function in 1011 for our structural degree of freedom x0 initially looks a little bit terrifying. Now it's convenient to group this into 4 parts. We have the real part of the numerator, that would be A. Then we will have the imaginary part, that could be B. In the denominator we have a real part here that we can refer to as C, and we will have a corresponding imaginary part that we refer to as D. So by this way of introducing real and imaginary parts, we can write the very lengthy expression in a somewhat shorter manner. Now, we are interested in the absolute value of x0. And remember that if you have a complex denominator, you multiply both denominator and numerator by the complex conjugate of your denominator. And by that, the denominator becomes the real part squared plus the imaginary part squared. And it actually turns out that the real part can be written in a corresponding nice way, things reduce, and thereby the amplitude squared can be written as in the second equation of 1014. Now, for the magnitude of this expression in 1014 to be independent of theta d, then we actually need to fulfill the following relation, namely that the ratio between the two real parts squared must be equal to the ratio between the two imaginary coefficients. So we take the square root on both sides, and remember, whenever you take the square root, you need a plus and minus. Then you go back and fetch your A, your B, your C, and your D from the original expression in 1011. That is this main expression here. You plug those coefficients into this expression, simple expression up here, and that provides you with 1017. Now we want to solve for omega, and it turns out if you choose the plus, you will actually only get the static solution for omega equal to 0. And that is of course not of interest. So therefore we choose the minus sign, that's the lower sign value here, and we then rewrite the equation as a second order equation in omega, or a quadratic equation in omega squared. So this is a quadratic equation in omega squared. Here we have omega to the power of 4, here are terms omega to the power of 2, and here we have the single constant term omega to the power of 0. So the roots to this equation are actually the frequencies for our neutral points omega A and omega B. These are the points that we can see on this curve here. So down here we have omega A over omega 0, and here we have omega B over omega 0. So based on these neutral point frequency, we have our first design condition. Make sure that the amplitude in A is equal to the amplitude in B, and that I have indicated in the bottom, in the left figure just below. So here you can see that somehow I have chosen a parameter so that A and B are exactly at the same amplitude level. And because A and B are independent, let's just write that, A and B are independent of theta d, that means that the condition should provide us with an optimal stiffness, TMD stiffness. And the optimal condition, I can already reveal now, is fairly simple, and it's given as the structural frequency divided by 1 plus the mass ratio. And this we obtain by having the same amplitude at the two neutral frequencies. Let's go back to our main equation, 1011. It's already quite tattooed, but in this expression, if we assume that theta d approaches infinity, then the B term will dominate the A term, and the D term will dominate the C term. So the two terms that are left are the two damping terms. And in these two damping terms, we can cancel 2i theta d omega because they're common in the two terms. And what is left is a very simple expression once we have divided by omega 0 squared. So the frequency response function for the structure reduces to 1019 once theta d approaches infinity. We can have chosen any other value for theta d. It doesn't really matter because the amplitude at A and B is independent of theta d. So here we simply choose the value of theta d, that's infinity, that provides us with the simplest expression. Now, we are actually looking for absolute values of the expression in 1019. And that means in the expression for 1019, we can either have that x0 at A is equal to x0 at B, or we could have it that x0 at A is equal to minus x0 at B, because once we take the absolute values, these two expressions mean the same thing. Now, I bet every one of you would try the plus version first, but you would find out that you wouldn't get a satisfactory solution. You will actually only get the trivial solution. So therefore, it is still and again the minus that is introduced. So the frequency response solution in A is equal to minus the frequency response solution in B. And if you solve this, you find that the sum of omega A squared plus and omega B squared is equal to 2 times 2 divided by 1 plus the mass ratio mu. We are actually not explicitly looking for the solution neither to omega A and omega B in this case. And the reason for that is that we know that omega A and omega B are the roots to this quadratic equation. And the sum of the roots of a quadratic equation is equal to the intermediate term divided by the factor to the quadratic term. And this is expressed here in 1021. So now we have two expressions for the sum of omega A squared and omega B squared. We have the solution from the roots of the quadratic equation, and we have a solution based on our design condition, namely that the amplitude should be the same in A and B. So we carry on this 2 divided by 1 plus mu, and we equal that to the right hand side of this expression here. Then we divide by 2, we multiply by 2 plus mu, and then we get the expression given here in 1022. And the only unknown in this expression is omega d. It's fairly easy to solve for omega d and get the solution that I have already told you, namely that the TMD frequency is equal to the modal frequency divided by 1 plus the mass ratio of our TMD. Now, omega d squared is equal to k over m, omega 0 squared is equal to k0 over m0, and they should be equal to 1 divided by 1 plus mu squared. We get that from 1023. And that means if we have the optimal TMD frequency, it's quite easy to derive the optimal TMD stiffness. So once you've decided on the mass ratio mu, you can go out and buy yourself some springs with this optimal spring stiffness K. For mass ratios much smaller than unity, you see that the so-called stiffness ratio is basically equal to the mass ratio. So therefore, there is a nice balance between stiffness and mass for the TMD compared to the stiffness and mass of the structure. So they resonate basically at the same frequency. But the TMD resonates at a frequency that is slightly smaller than omega d for positive value of our mass ratio. Let's go back to our equation 1018 that determines the two neutral point frequencies, omega A and omega B. Now we know the value for omega d. So we can actually substitute that into our expression and then find expressions for omega A and omega B. That means if you substitute in omega d by this simple expression that we have from the frequency tuning on the previous slide, we can reduce our quadratic equation that provides us with omega A and omega B. You find the discriminant, you set up the solution, and it turns out it can be written in a fairly simple solution where we have a plus minus by the solution expression for quadratic equations. So we take these omega A's and omega B frequencies and we plug them into our expression for the frequency response function, because this solution for x0 was exactly obtained for omega d approaching infinity, so it represents the amplitude at A and B. And if we do so, we get this solution here, and we substitute in our solution for omega A and omega B. Things cancel, and we get plus minus the square root of 2 plus mu divided by mu. And we are really happy to see this plus minus here in front, because we would like to take the absolute value. So the plus and the minus simply refers to either being above or below the resonance frequency, and it vanishes once we take these absolute values. And therefore, we get this final solution for the dynamic amplification factor at the two neutral frequencies. And if we take a look at my green line on this structure here, we find that the value is the square root of 2 plus mu divided by mu. So for small mass ratios, which we typically assume, we get that the value is then equal to 2 divided by mu. And that means it's proportional to 1 divided by square root of mu. So if we want to bring this level down, we should then increase mu. So let's assume you know a certain level of dynamic amplification equal to some kind of level. And this level you can then set equal to 2 plus mu divided by mu, and that provides you with a desired value for the mass ratio. Once you know the mass ratio, you can find K from omega D equal to omega 0 divided by 1 plus mu. And the only question we have left is, what about the damping parameter? Now, if you look at the upper left figure, it's nice to have the same amplitude in A and B. But for the black curves, we have large amplitudes at the two original resonant peaks. And for the red curve, we have a very large amplitude at omega 0. So the black curve was for 0 damping, the red curve was for 30% damping. But look at the blue curve. The blue curve was for 10% damping. And it has a slight overshoot just outside the omega A and omega B parameter frequencies, but inside it has a very small value. So thinking of the waterbed effect, one could argue that what if we could bring up this intermediate value? Could we then bring down these two outside resonant peaks and thereby get an even better and flatter curve? And of course we should remember that somewhere in between here we have the point C, and the point C was the crossing point in the right figure for the damper response, and the omega C point was at, or the point C was at omega infinity. So what if we could have the amplitude at A equal to the amplitude at B, but in between at the intermediate frequency C, what if we could also bring the amplitude to be equal to the A and B amplitude? Wouldn't we then get an almost optimal flat plateau in the frequency response function? Let's follow that procedure. So our omega infinity is given as omega 0 divided by the square root of omega 1 plus mu. And if we substitute in our omega d instead of the mass ratio mu, we find out that omega infinity is actually the so-called geometric mean of the omega 0 frequency and the omega d frequency. The point C in the curve is defined at omega infinity. So what we do is that we go back to our frequency response function, and we then take a look at the frequency at omega infinity. Or rather, we plug in omega equal to omega infinity. And if we do so, many things cancel, and we get a very neat expression for the frequency response function. Then we take the absolute value of that. That basically means the square of the real part, followed by the square of the imaginary part, and we should of course divide by the square of the denominator, and that provides us with this expression here. Now then we take the expression in 1030 at the infinity frequency, and we equal that to the amplitude at the two A and B frequencies. And this amplitude we have from the previous slide right here. The math is very simple, and we get this expression here for the optimal zeta d, and we refer to that as zeta optimal in the following. Then we go back and have a look at the definition of how zeta is defined, and we resolve from zeta d a corresponding optimal value for the damping parameter, that is c. Just to get the notation right, that c was actually without the subscript d. So now we have an expression for the viscous parameter that we should go out and find a damping device for, and once we've done that, we hope that we get a flat plateau in the frequency response curve. Now, an alternative optimality criteria was proposed many years ago by Brock and summarized by Den Hartog in his very famous mechanical vibration book. And basically that principle says that what if we get a horizontal tangent at A, and we get a horizontal tangent at B, and then we find the damping parameter based on an average of these two conditions. And it turns out that this expression gives us 3/8 instead of 4/8. So the classic Den Hartog solution is slightly smaller than the present optimality condition. So if we have a look at the optimal dynamic amplification factor, the blue curve represents the solution with zeta d equal to zeta opt, whereas the black curve represents zeta d equal to the Den Hartog solution that we refer to as classic. And it turns out that the maximum amplitudes occur at A and B. The Den Hartog solution has an intermediate reduction of the amplitude, which we do not see for our proposed application. And then one would say, okay, why don't we use the Den Hartog solution, the classic solution, instead of the present optimal solution? And the answer you can see is in the figure to the right, because the Den Hartog solution has two peaks in the damper response, slightly outside the reference frequency at point C, whereas our optimum, the blue optimum, is exactly flat in the damper response curve. So we claim that we get a flat curve in both the structural response and in the absorber or TMD response. And the mix between the two provides us with a nice balanced optimal tuning of our TMD. Based on our solution, we already have a well-established expression for the amplitude of x0, of course, when we divide by the static solution, and that was square root 2 plus mu divided by mu. And that was for A, C, and B. Now, from the XD solution, we would like to get an equivalent, similar expression for the amplitude at C, because A and B are really structural response values, but in the curve to the right, we only have the reference frequency at C. And at C, that means for omega equal to omega infinity, we can, from the frequency response solution to XD, that's the one we have in this expression here, we can find a very nice expression here in the blue box for the dynamic amplification at XD. And it turns out is given as 1 plus mu divided by mu. And that means at C, we could try to make the comparison between XD and X0. So that gives me 1 plus mu divided by mu, and then we will have the square root of 2 plus mu divided by mu. And if we put in a large square root, we will get mu, and then the 1 plus mu must be squared, divided by mu squared, and 2 plus mu. Now, if we assume that mu is much smaller than unity and also 2, then we can cancel these two mu's inside the parenthesis, and this one will cancel with the number 2, and then we will have that we get 1 divided by 2 times mu, and that's approximate for small values of mu. And let's put in our value of 5% critical damping. So that is for mu, just as a reference case, we will have xt divided by x0, of course, absolute values. Remember those. Will then be 1 divided by 2 times 0.05. That's square root 10. That's approximately 3.1 or 2 or something like that. So this shows that if we have a desired amplitude for x0, let's say 40 centimeters for vibrations of our pedestrian bridge for a given loading, then we should multiply these 40 centimeters or 4 centimeters or whatever it is by a factor of 3.2, and we should make sure that inside our bridge deck we have sufficient space to actually carry this fairly large TMD vibration amplitude. Let's have a look at a fairly simple example. We take our 4-story portal frame structure that we also considered in our modal analysis, and we then apply a force given by these F values here that is identical for each floor. So our force vector as function of time is equal to F of t, then we have 1, 1, 1, and 1, and we assume its harmonic force omega t. So we apply some kind of intensity, and this intensity we can actually represent by some kind of intensity value f0. So that means our f function over here is equal to an intensity f0 times sine omega t. And we simply apply this load on each of our 4 floors, representing the 4 unit values in this vector. Then we also introduce our tuned mass damper. So it is governed by the TMD mass m, and we then find the mass ratio in terms of the modal mass when we normalize top deflection to unity, and based on the mass ratio mu, we can find omega d to give us k and zeta d to give us c. Now I want to run some simulations to show you the correspondence or the similarity between a frequency response analysis with a dynamic amplification curve as a result, and then time simulations that I have been conducting using the Newmark method that we're going to consider in the next lecture. Now I have 5 degrees of freedom in my equation of motion. And therefore I have introduced these tilde vectors for the degrees of freedom. We have that the 4 regular stories are represented in the regular q vector, whereas the deflection of our damper is given by u. And I think in the figure it's referred to as ud, like this. And then I set up my mass matrix. In the upper left part you will see the mass matrix of the structure. So this is a 4 times 4 matrix, and down here we have the mass of the TMD. For the stiffness, we have the stiffness matrix of our structure, and then we add the stiffness of the TMD by a so-called connectivity vector. And this connectivity vector is a unit vector, or 0 vector, with a single unit value exactly at the degree of freedom where the TMD is attached. And in our case, the TMD is attached at the 4th floor, and that means the 4th entry in W should be equal to unity. And by that we can move the TMD up and down, all depending on where this unity value is placed in the connectivity vector. And the connectivity vector, of course, defines the deflection of our structure, and this is not correct. I will provide you with a revised version, but Q4 is equal to the connectivity vector multiplied by the original degree of freedom vector, that was the one without the tilde. So we add the structural stiffness, or the TMD stiffness, to the structural stiffness matrix in the upper left part. Then we also have coupling with the TMD, and the TMD itself will get the stiffness K. And the damping matrix is constructed in just in the same way, where we, as in the calibration, will neglect any structural damping in this case. Now, I run my simulations with a forcing frequency that is equal to my omega 0 frequency, and because we are damping the first mode, it's equal to omega 1 from my modal analysis of the 4-story portal frame structure. So I normalize my curves by omega 0. The figure to the left shows the dynamic amplification curve for x0. At resonance, we see that the amplitude is about 6, or the dynamic amplification is about 6, and of course we get a slightly smaller amplitude if we excite it a little bit less than omega 0, but in principle, around the resonance frequency in this, let's say, bandwidth here, we will have an approximate flat plateau that is represented by this curve here. And remember that the dynamic amplification here is 2 mu divided by mu. And by calculating this value, we find 6.4 or square root 41. So the dynamic amplification factor is 6.4. Now in the next figure, this one here, I now run my Newmark. Let's just start over. Nathan Newmark was his name, and I use this for my time simulation. And I need to use Newmark simulation or some other kind of time integration procedure, because modal analysis is not applicable anymore, because the presence of the damping and the stiffness will violate my orthogonality conditions. And you can see in the beginning I have an increasing resonant build-up of resonant. I have a slight overshoot here, but basically I end up at my steady state amplitude quite fast, because I have fairly much damping in my system because of the TMD. Now my response is plotted for the top floor. So Q4 is equal to the top floor. And then I realized that dynamic amplification is dynamic response divided by static response. So I calculate my Q static response as only by the stiffness matrix multiplied by my F0 amplitude. And basically F0, and then I could have my 1, 2, my 4 ones here. And from this, I take my Q stat, and then of course the fourth entry, because that's the static deflection at my top floor. And I divide my dynamic response by that. And then you see I get actually exact my 6.4 dynamic amplification value as indicated by this red line here in my curve. So you should always think of a point in a frequency response curve as a corresponding amplitude value during steady state. Let's see if it also works for the TMD response. So in the third figure, I have my amplitude of XD with the fully flat plateau here at my around my resonance frequency, and you can see we are at an amplitude slightly above 20. And we remember that the amplitude level, and there wasn't a square root, that's quite important, is 1 plus mu divided by mu, and in our case that's 21. Now if I take the difference between Q5 and I subtract, that's Q5 tilde, and I subtract Q4, that's the same as taking the absolute motion of my TMD minus the original Q4, and I'm pretty sure this value here should be UD. And I divide by the static deflection of my fourth floor again. You will see that I, at steady state, exactly get my value of 21. So again, it's quite easy by a frequency response analysis to immediately get an idea of what is the amplitude during steady state. And you know that for resonance, we have a minimum overshoot in our time response curve. So the steady state value is actually also very close to our maximum deflection. And that is why frequency response analysis by figure 1 and figure 3 are such a strong tool, because they, without using or simulating full time series, can actually provide us with amplitudes at resonance. And in many cases, we design our structure directly to resonance, assuming that we have an harmonic loading, time harmonic loading on our structure. Take the train to Østerport railway station. Go towards the Little Mermaid, and you will cross this pedestrian bridge here that was built now quite many years ago already. During the design stage, the architects decided to make a fairly slender design. You can see the height here is in the order of magnitude of 1 meter or something like that. And if you do not install dampers, you will have 4 to 5 vibration modes that are within the 5 Hz limit for pedestrian loading on pedestrian bridges. So these modes, they have to be damped, and the idea was to damp them by TMDs. A little bit of the length. Each of these spans are between 30 and 50 meters, and the total length is 170 meters for the bridge. And you can see it's approximately 1 meter height 1 meter, and width 7 meters, and around 560 tons. And these are the 4 frequencies below the 5 Hz critical limit proposed by standards for pedestrian structures. The analysis is then based on structural dynamics, and we assume the first vibration mode, or a given vibration mode, to be dominant. So remember that in this case we actually have 4 modes that need to be calibrated or tuned by TMDs. But we try to calibrate each of the TMDs independently with respect to their particular vibration mode. So for each of the first 4 modes, we find the modal mass and assume modal loading based on the concept that we have for modal analysis. Everything boils around the question, what is the mass ratio? Now, if we have several TMDs on our structure, it's quite complicated initially to say, okay, what's the total vibration mass by these TMDs? One approach is to construct a TMD mass matrix. And for a single TMD on a structure, you take a fully zero mass matrix and you add the mass of the TMD at the diagonal element corresponding to the location of your TMD. For a single TMD, you can represent this mass matrix by a connectivity vector with which you make this outer product, and then you multiply by the TMD mass. And that will give you an all-zero matrix with a single element that is non-zero in the diagonal exactly at the location of point of attachment of the TMD. Then you can set up the modal mass for this TMD mass matrix, and you can divide it by the corresponding modal mass for the structure. For the mass matrix, and there's a square in here, you'll get the connectivity multiplied by the mode-shape vector that gives you a scalar value for the amplitude of the structure at the location of the TMD. You square that scalar value, and if you remember, in most cases we will always normalize our modal deflection to unity at the location of mass, whereby this one becomes unity, and the mass ratio is equal to m divided by the modal mass, mj. Like this. So once we have the mass ratio for a given mode, we can calculate the corresponding viscous parameter by the optimal zeta relation, and we can find, this will give us C, and we can find the optimal stiffness from the expression for the optimal frequency. The 4 figures show the 4 modes, and the blue boxes indicate where TMDs have been placed to damp exactly these vibration modes. So that means we have 1, 2, 3, 4, 5, 6, 7 packages of TMDs located along the bridge. And the idea was to actually assume these 5% mass ratio for each of the modes, because that would give us 15% critical damping, and it actually turns out that the corresponding structural damping that you will get to a particular mode is approximately equal to half the damper damping. So that's an easy way to work in damping ratios. But of course it would also mean that we get dynamic amplification factors that are around these a value of 6, which is quite low and quite nice for resonant vibrations. The upper table then provides us with a design. So the upper table, we simply apply TMD masses, these 7 TMDs inside the bridge, so that we get mass ratio of 0.05. And as we saw, that should provide us the structural damping ratios in the order of 8%. Now, then we ran a full modal analysis for the damped structure, and we evaluated the damping ratio. That's beyond the content of this course. But it turns out that for the first mode we got two damping ratios. One was 6 and the other one was 10. Now the difference in these two damping ratios simply mean that for the first mode, first pick, we would get a large value because we have only 6% critical damping, while the other one would be somewhat more reduced because we will have 10% critical damping. And of course, the 8% we were looking for would result 8%, that means 7.7%, would reduce this left peak down to below the desired value. So somehow, because we now have 4 modes that needs to be damped by TMDs, there's a certain modal interaction between these modes, and that kind of destroys our desired calibration. For the next mode, we are above 8, and for the fourth mode, we actually get a very nice and balanced design. But the problem is, of course, mode number 1, that seems to be deteriorated by the modal interaction. What was then done was a step 2, a correction, where we simply repeated the modal analysis, but for each of the modes, we included the damper mode. So we simply assumed on the bridge deck that we now attached at the different points the TMD masses, the 7 TMD masses that we applied on the bridge. And then we simply ran the procedure one more time. And it turns out that for mode number 1, which was the critical one, we now suddenly got much closer to our desired 8%. And that solved the problem. And this concludes today's lecture on TMDs. Have a look at the summaries, go through the video slowly, and try to pin down and identify the important design parameters. And in the reports, we will of course also work with design of TMDs.